Hello everybody, welcome to this session where we will talk about memory hierarchies, technologies and interconnects that enable new system solutions for large-scale applications. I'm Manoj Wadekar and I work at Facebook, and I'll be presenting this session along with Reddy from Intel. So let's dive just right in. Well, almost. Please take a moment to consider the legal notice and disclaimers. We are roughly dividing today's agenda in two parts. I'll walk through the rationale and goals for this work for software-defined memory and introduce work the OCP or Open Compute Project has kicked off in this area. Then look at architectural nomenclature and logical system representation of memory technologies, interconnects for various applications while using hierarchical memory. I will then hand off to Reddy to cover the remaining part, which is software representation for this architecture and one example benchmark to demonstrate the value of this new paradigm brings to the caching applications. So let me provide a background and overview of the SDM workstream, the software-defined memory workstream within Open Compute Project, OCP, that we kicked off earlier this year. As you know, OCP brings benefits of open source and open collaboration to hardware and rapidly increases the pace of innovation in, near, and around the data centers. So earlier this year, a new forum was created within OCP. It's called Future Technologies Initiative, with a goal to be early part of that funnel that drives innovation to the OCP platform by connecting leading use cases to innovative technologies and thereby contributing to the priorities for industry, research, and academia. So FTI focused on three areas this year: software-defined memory, which is the topic for this presentation, cloud service model, and AI hardware software design collaboration. We are here to talk to this all storage specialists in the world here and join hands for driving adoption of hierarchical hybrid memory solutions. With this in mind, SDM team has focused on three things. Number one is to map the key applications for driving these new memory hierarchies. And then second, articulate the logical architecture for such systems. And third, more importantly, contribute benchmarks so that one can enable the validation of novel ideas for key applications in such systems. So these are the three things that we want to focus in SDM: survey and define the right applications, establish the architecture, and make sure that we have the benchmarks identified to evaluate various architectures and for efficacy for those applications. Now going into the software-defined memory and seeing what that is. So software-defined memory is focusing on future systems that can allow software abstraction between applications and underlying memory resources that offer flexibility to the applications to expand memory footprint to achieve the desired SLA or goals. There may be capacity need or there may be performance need. And so how to take those hardware system components and software connectivity to the applications to achieve that memory expansion goal or hierarchical goal. So we'll look into our early view into such abstraction from logical hardware perspective as well as the software perspective. So please allow me to establish the nomenclature for various system blocks in such a hierarchy. Now the system may be focused on CPU or a GPU or accelerator that needs additional memory for performance or capacity needs. The first level memory is something that is connected natively to processing unit and remains primary preference for application placement. Type of memory and interconnects are going to vary too, covering from DDR family or DDR3, 4, 5, or for high performance memories that are connected through those buses, for example, HBM, etc. So these are going to be all first level memory. Then you have second level memory. Those all the memory that is, of course, it's clear from the naming, it is memory, so it's going to be a load store interface. And it is of a secondary preference for data placement for the applications. The secondary preference could be due to different type of memory media. It could be older generation of DRAM as compared to the first level memory, or it could be storage class memory, or it could be different interconnect, for example, CXL, Gen Z, or any other interconnect, or it could be software abstraction like compressed memory, for like ZSwap or etc., which allows you to choose between the primary and a secondary placement point of view. So that becomes a second level memory. There is a third type of memory expansion mechanism that is available and used today, and that is using block devices. So these are not load store devices, these are block devices like NVMe storage, and they use software modules to access this block or file devices to get the memory expansion functionality. So these are the three types of ways you can achieve the memory expansion for the systems, whether through first level memory, through natively connected, second level memory, which may be connected through the different interconnect or through software abstraction or different type of media. And the third type could be really going to the different types of connectivity for block storage. As we look into expanding memory through hierarchy, now the important question is that who is going to benefit from it? What are the key leading applications? So obviously, in-memory databases and in-memory analytics come to mind. They do benefit from higher memory footprint and efficient mechanism to access that memory footprint. ML or machine learning or deep learning workloads are also very expanding fast, and the need for high performance is very high, as well as the high capacity memory for scaling the models for these workloads. So whether it is because of scale up within the system or whether it is scale out across multiple systems. So this is of course driving the very high demand for the memory expansion. A multi-tenant memory or the virtualized environment is also very well known for allowing you to scaling up of the memory is important so that we can efficiently use the platform when we virtualize it or have multiple tenants running on it. So as we look into all these applications, including high performance computing, let's talk about some system designs that address above applications and map the hierarchical memory nomenclature that we defined in the previous slide to such systems. So when a system has only natively connected memory, you may have just natively connected DDR memory, or DDR4 or 5, but if it is managed through two different pools. It could be high performance memory, that is primary memory for applications, but there could be additional memory which is compressed memory that may be maintaining colder pages through Z-swap kind of mechanisms. So in this case, one could say that the first memory is going to be the pool that is using the first level memory uncompressed is your the primary choice for the placement, and then the colder memory being into the compressed memory, that becomes your second level memory from application perspective. So you got a first level memory and second level memory even if the pool was just natively connected. The interconnects like Accel that are coming now are enabling expanding the memory in a cache coherent fashion. So in this case, the memory attached to Accel will be considered as a second level memory. Now, of course, we are aware of basically multi-socket configurations where you have different interfaces connecting multiple sockets, where you could say natively connected memory for that socket is going to be 1LM, and the remote socket through other buses could be UPI, QPI kind of buses could become a second level memory for which is connected to the second socket. The example that we are not shown here. So memory that is natively connected is a primary memory and hence 1LM memory. Databases, caching applications, multi-tenant applications, all of this can use above systems for expanding the memory capacity. We'll discuss this more in the details soon in the later slides. Well, let's go to the second example where there is a system that is composed for the GPU or accelerators. In this case, focus for the system is in the GPU and it is provided all the models, etc., information, features, etc., through the CPU. But focus is, of course, for GPU applications, the memory that is connected, the native memory is going to be high performance memory like HBM. And the memory that is accessed through CPU will be treated as a second level memory. So GPUs could be accessing such memory through either PCIe or CXL or any other interconnects that the system may have. And that becomes second level memory. The first level memory is the natively connected like HBM. So this is the picture for the system for the GPU and accelerator using the same mechanism. New growing use cases for expanding the memory of applications that are scaling up as well as scaling out. So in this case, they may benefit from expanding the memory within the system locally, as we discussed in the previous slides, but also pooling or sharing memory across interconnects like CXL or Gen Z. In this case, pooled memory is going to be considered as a 2LM from that CPU perspective or a GPU perspective. Now, this can be there can be multiple hybrid combinations of these three types that we talked about: CPU perspective, GPU perspective as pooled configurations that we looked at into last 3 slides. There could be multiple hybrid combinations. However, the important aspect now that comes up is that now that we talked about hardware blocks in a logical fashion and how to put together for different kind of system designs, how is this memory going to be presented to the applications? What are the options for data placement? And how does one compare benefits to the applications of these various options? So For that, please allow me to invite Reddy to talk through this. Reddy?
Thanks, Manoj, for the SDM intro. I'm going to cover the software view of the SDM architecture. There are two different ways of actually consuming, the memory hierarchy deployed and attached to the platform or visible to the platform. One is through the kernel managed placement. So kernel manages the one element, two element media, and then exposes that to the application using the uniform virtual address space. And then application uses the malloc and free. That's one way to consume the memory. The second way to consume the memory is the application actually manages the placement between one element, two LM, and implements the tiering policies that that are fairly advanced in nature, and then it can benefit from some of the fine-grained control of managing the 2LM media. So in the right-hand side, the example, the application managed placement, it basically uses the malloc to access the 1LM. And for 2LM, it has the native integration to access the 2LM media through the load store semantics. And I will cover details of what are the different ways of accessing the 2LM media. But that's essentially how application can actually manage the 1LM and 2LM to do its own implementation. Right. So those are the two different ways of consuming the memory hierarchy. Now, typically when the memory is actually attached, specifically the 2LM, when the 2LM could be coming from the CXL attached memory buffer. CXL stands for Compute Express Link for some of you who haven't heard about CXL. Storage class memory like Optane PMEM attached to the host platform, or storage class memory attached to the CXL. They are actually exposed as the logical NUMA domains in the kernel. What it does is it essentially gives you a way to consume the media directly through the NUMA framework that is available in the operating system. Or you can actually use, user space heap manager libraries like Memcached as a way to actually access the 2LM memory directly. Obviously, the third way is to actually consume that through the kernel managed, like we talked in the previous slide. Right? So there were different ways of actually consuming the memory, but they're all visible using the logical NUMA domains. So, so let's take a look at the Linux kernel memory tiering as one example of how we can consume the memory that is available in a platform. So if the server has 1LM, 2LM memory, the kernel manager can actually manage both types of memory transparently. And then, of course, through the page caching, can actually provide a consistent view of the capacity, aggregate capacity, using the virtual address space that application can actually consume. So in this case, the application does not have to change. So it will continue to use the malloc and free as one uniform address space. But behind the scenes, the kernel is actually managing the both types of media and migrating the data between the 1LM and 2LM based on the access patterns and hot versus cold data. So the current kernel implementation has a mechanism to demote when the page actually gets evicted from first level memory. In this case, it is the host DRAM into the second level memory. The promotion aspect from second level memory when it becomes hot to the first level memory is still being worked out. And then of course all the advanced policies that kernel can use to do the sophisticated tiering is something that requires a lot of work in the kernel community. There is a downside. While the upside is that there is a uniform virtual address space that gets presented to the application, and then application does not need any changes. The downside is that the actual migration of hot and cold data between the tiers does have impact on the performance because it takes compute cycles. And then obviously, the copies require TLB flushes. That also impacts the performance, right? So there is a downside, but the upside is that you don't need to make changes to the application, which is fairly significant. So that's one way of consuming the memory, different types of memory in a platform. Do note that the kernel memory tiering is fairly early from a maturity perspective. It is expected to evolve with very sophisticated tiering implementations over the course of time. On the elements of how do you manage different types of memory, specifically the NVM type of memory, and then how that gets consumed, how that gets bubbled up through the kernel drivers and consumed in application. There is a standard spec available from SNIA, which is called SNIA NVM programming model. This example shows the PMEM, but that scope includes broader NVM media management. It includes elements of how to manage the media through the management library and the API spec. And then it also includes the details of how applications can consume the NVM media using different block and load store semantics. So if you have an application that uses the block mode today, you can consume the NVM media through the standard raw device access. Right, that's one way of consuming it. It may not be optimal, but you don't need to make the changes to the application because it is using the storage semantics. If you have an application that uses a standard file API, open, read, write, close, store type of file system API, POSIX file system API, you can use the the standard file system route. Now, Linux kernel has a mechanism to support the file system API through PMEM-aware file system for persistent memory. In this PMEM-aware file system, essentially you can mount, obtain PMEM type of media through FSDAX extensions, and then you can actually read and write in that file system. The difference between these file system from a legacy perspective versus PMEM-aware for the obtained PMEM media is that PMEM-aware file system does not use the page cache because it knows that the media behind is also a memory media, not SSD, which is block-based slow device or hard disk drive as another example. So PMEM-aware file system is a mode where you typically use for the obtain PMEM or persistent memory type of media where you don't want to actually consume the page cache, which is at a premium. The last but not least, if an application wants to take advantage of the last ounce of performance and latency attributes of the NVIDIA media, it can use the load store API and directly manage the read and write from the NVM media without actually incurring the latency penalty that kernel brings onto the table. So, so in summary, you can essentially use the block mode or the file mode or the memory mode for the NVM media, either through the kernel driver interface or organically through the native load store API. Right. So this is the SNIA programming model. Let's take a look at how we can actually use the load store API for the NVDIMMs using Memcached library. Memcached is the library that is open source It's the app user space heap manager that you can actually use, which is extensible, that essentially takes advantage of the gmalloc hooks. And different 2LM types are actually called kinds of memory in the Libmemkind. So you may have a capacity oriented, you may have a latency oriented, you have a storage class memory, right? You have CXL attached memory. They're all different kinds of memory. There are hooks in place in the Libmemkind that can actually take advantage of those kinds of memory and allocate using the slightly modified, the malloc and free calls to take, consume the memory, from the 2LM media. And, you essentially can have multiple pools of memory, and then you can actually manage the tiering on top of the Memkind library in your application, whether it's DRAM or it's high bandwidth memory or persistent memory or CXL attached memory. You can have multiple pools and you can manage the tiering, and you can implement very sophisticated policies in the application and then consume it that way. PMEMkind is one example. In the PMEMkind, there are different PMEMkind hooks available in the Libmemkind. One of them is the file back, where a temporary file is actually created and it's memory mapped, and then you can actually issue the malloc and free calls on top of that. The key difference here is that this is used and treated as memory, so there is no persistence on top of that. So whenever application actually exits, you essentially lose that. There is no persistence, and then you lose that capacity. Right? It can be allocated for somebody else, and the content is overwritten. So the kernel construct as part of the Libmemkind. So the Linux kernel has the capability to configure DevDAX, PMEM media, or NVDIM media, and essentially expose that as a logical NUMA node. LibPMEM has a type called Memkind DAX KMEM, which is essentially kernel exposed memory using the logical NUMA domain, and then you can actually consume the memory using that mode via a Libmemkind library as well. So that hopefully that gives you an idea of how the kernel managed tiering can works to expose different types of memory hierarchy transparently to the application, as well as deeper application level integration using a SNIA programming model, PMDK, or using a Libmemkind library to manage different kinds of memory in the application to do advanced tiering. Let's take a look at a benchmark that essentially highlights how different types of tiers and configurations can actually impact the performance. And we will use the CacheLib as an example. So CacheLib is the pluggable, in-process caching engine that manages the tiering automatically. Currently, CacheLib has support for DRAM and block, for NVM. It is somewhat suboptimal for PMEM, but we'll show you the data on how, how that performance is. This is actually open source by Facebook recently, and it is extensively used by Facebook in the cache, in the Facebook data center, service deployments that are hosted by Facebook for their internal services rather. CacheBench is the benchmarking tool that uses the CacheLib API for evaluating different types of media, right? Different types of media, different configurations, and how does the CacheLib, to evaluate the performance attributes, we can use the CacheBench as the benchmarking tool. So both of these are actually open sourced, and it's available in the GitHub location that's in the last bullet. The test configuration, this is the Cooper Lake processor, 26 core, single socket. The board is actually the open compute board called Delta Lake that has a support for 12-volt power rail, support for the NVDIMM, for Optane PMEM specifically. This board has 6 channels, 1 DIMM per channel configuration. We have 4 DDR4 modules, 16 GB capacity, and then 2 Optane PMEM 200 series modules, 128 GB capacity. BIOS does require some changes to support the PMEM. And then the operating system we used is the Ubuntu 18.04. Here is the performance data between 3 different configurations. So the 1LM DRAM uses only the host DRAM capacity. The 2LM MEM is the platform 2LM configuration that is available on the Cooper Lake generation, where it exposes the Optane PMEM as basically the memory to the operating system, where it uses the DRAM cache in the front. And we are using 225 GB capacity for 2LM memory mode. And then 2LM CacheLib doesn't have native PMEM support. So we are using the block interface in the CacheLib, and we are calling that as the 2LM PMEM block configuration, where we are using the 32 GB DRAM capacity, and then we are using the dipper size NB, which is 188 GB, which is the dev PMEM capacity. Right, so we do get the 2LM functionality out of CacheLib. However, it is slower compared to native platform 2LM, which manages the tiering transparently via the platform, caching. And then 1LM is purely your baseline from a performance perspective. So we should expect 1LM to give the best possible performance, which is what you see in the first graph, number of gets per second. This essentially is the key benchmark for caching workloads. So key metric rather, sorry. So the 1LM DRAM gives the best possible throughput, number of gets per second, and then the 2LM memory mode comes very close to DRAM, which is not bad because you're essentially using the higher capacity media compared to the DRAM, which is and less expensive, right? So combination of those two is what you get the additional capacity as well, where you can actually get the better hit ratio on top of that. 2LM PMEM block is slower. You should expect that primarily because it uses the kernel block layer and then hits the PMEM media, so which is significantly slower compared to the 2LM memory mode. The latency, obviously the DRAM gives the best possible latency. The 2LM memory is somewhat higher, which is expected because whenever there is a miss, it is accessing the PMEM data and promoting it to the cache and then actually servicing that from the cache. So we expect certain delay and lag. Block has the highest latency primarily because you have the block IO, overhead, kernel driver overhead on top of that. The hit ratio is somewhat, higher with the 2LM, primarily because you have higher capacity. The total number of items is also higher on the 2LM, primarily because you have higher capacity, so you can store a lot more items compared to the DRAM, which has the smallest capacity. So this essentially gives you a flavor of different modes with application implementation like CacheBench that has the tiering implementation. How does it compare and contrast from the highest performance to the block mode, which is really the least intrusive change, but it doesn't give you the best possible performance. So application changes, having a software stack that actually can take advantage of tiering with different types of media is extremely important. This is something that we will work through in the cache lib community to enable PMEM native interface as well, so we can exploit the bandwidth characteristics. So that's the CacheBench and CacheLib performance data with Optane PMEM to just give you the flavor of how we can use the existing software stacks like CacheLib as a way to get the transparent tiering and be able to consume 1LM to LM media. So in summary, Manoj actually talked about software-defined memory initiative under the umbrella of Open Compute Future Technology Initiative. This is primarily focused on what are the specific applications that can actually benefit from memory hierarchy. What is the best way to evolve the architecture, software-defined memory architecture that manages the heterogeneous, the memory. One, that is available within the platform. Two, that is available as the pooled memory. How do you carve it out, and how do you consume that transparently or through application, libraries? And the architecture revolving around that is something that we need to go define. And then, of course, we need to have the benchmarking tools that can support memory hierarchy solutions that are emerging. Now, why do we need this? There are several changes that are happening in the industry, specifically within the context of open interconnect standards like computing, ExpressLink. There are also media, lots of different types of media that is evolving, including storage class memory, high bandwidth memory. If you take a combination of open industry standard interconnect and the different type of media, you will end up actually having different performance, latency, and bandwidth characteristics that you can actually attach to the platform. Plus the memory and resource pooling on top of that. Combination of all these things require us to rethink how we need to build and evolve software-defined memory architecture and drive that cohesively as part of the common industry effort. And then, of course, consuming these memory resources in the application is the most important element. Transparently, whether it is actually managed through the kernel or whether it is managed through the application libraries, is something that we have to focus and evolve so that we can address the broad spectrum of workload requirements. That's really what we will be focusing on going forward within the context of SDM and OCP Future Technology Initiative umbrella. With that, thank you for your time. Please give us a feedback and let us know. Thank you.